Hi everyone. In this video we're going to look at the derivation for the formula for the volume of a sphere. So first we've got the sphere with radius capital R on the left here. And to make our lives a little easier, we're only going to consider one half of the sphere, which means a hemisphere. Now what's interesting about this is the picture we'd have is the following. We'd have something like that. And this image is actually derived from this particular shape rotated about the y-axis, okay? Now this particular shape that you're looking at here actually is a circle, okay, which is where this equation is coming from. So x squared plus y squared equals capital R squared is the equation of a circle centered at 0, 0 with radius big R. Okay, so no big deal there. Now, because we are taking this particular shape and rotating it around the y-axis, this means that our horizontal cross-sections have to be in terms of y in this case, okay? So what I have to do then is solve this formula, x squared plus y squared equals r squared, for x. Now, I know it's a little strange because we also have a capital R in here. You have to remember that R is a number, okay? It's the radius of this particular sphere. So it's a number like 6 or 7 or square root of 4, something along those lines. So anyway, this is the formula then in terms of y. Now, you may be wondering, why is that important? Well, we have to remember that the cross-sectional formula has to be written in terms of y. A of y is equal to pi r squared. Okay, so in this particular case, what we're going to use is we're going to take r to be equal to this square root of r squared minus y squared. So we're just simply replacing x with a smaller radius just for the sake of this formula here. Okay, so we need to substitute that in and simplify. And squaring this actually removes the square root. And so we're left with pi times r squared minus y squared. So now what we do is, to get the volume, is we take the integral of this particular area function with respect to y. And now the bounds. Now we know the bounds are going to go from 0. Okay, again, we're looking at this piece here. So the question is, what does it go up to? So what is the point of intersection with the y-axis? Well, in fact, it is r, right? So this whole distance here is r. And so that's why the bounds are going to go from 0 to r. So remember, we don't have a specific number because this has to work for all spheres, okay? So a little strange, All right, so what we need to do is some simplification here. So this should be the integral from 0 to r of pi r squared minus pi y squared dy. And the pi r squared, remember, is a number. Okay, that's very, very important, especially when we take the integral. Okay, so let's see what we get. This will be equal to pi r squared y minus pi y cubed over 3, and we evaluate this from 0 to r. So don't forget, 0 r squared is a number, so the antiderivative of that, you include the variable, right? So it's no different than if we were asking to find the integral of 3. That would just simply be 3x, okay? So no big deal there. And then taking the antiderivative of pi y squared, we add 1 to the exponent, so that's going to give us y cubed, and we have to divide by that exponential power. Okay. Now what we do is we substitute in capital R for y, so that's going to give us pi r cubed minus pi over 3 r cubed, and then of course we know minus 0. Okay. And then we clean up this formula, which is going to give us, let's see, pi minus pi over 3 is going to be 2 pi over 3 r cubed. And so that's the volume, remember, of the hemisphere. So that's only half of the sphere. And so to get the entire sphere, so the volume here of the entire sphere, you simply multiply this by 2. So that's going to be 2 pi over 3 times r cubed. And that gives us the known formula of 4/3 pi r cubed. So that shows you how you can use calculus to derive the formula for the volume of a sphere.